Hello and welcome back. So this video is for class 12 and today we will start with a new chapter, that is alternating current. Now I am sure you remember the concept of alternating current which we had studied in 10th class. But still, just so that we remember it very well, we will see a very short introduction about alternating current, because that is what we are going to study in this entire chapter. So to understand alternating current, first let us understand direct current. Okay, we know that there are two types. One is direct current, the other is the alternating current. Now you know direct current. Okay, basically the cell that we are using in our households, that is in our remote controls, then in our watches, right, in our mobile phones, that cell that is using that is producing a direct current. So let us say we have a resistor, and to that resistor we connect a cell. Okay, now this cell is a direct current. How you know it is a direct current? Because of the symbol. Okay, when we draw a cell like this, it is a DC power supply, a direct current power supply. Let me write this point as A and this point as B. Now, because this is a direct current, what will happen is current will start moving from the positive end and move towards the negative end. That is, the electric current will go from point A to point B, right? How much current will go? We know the current that will go is capital I, which will depend upon the resistance R and the voltage V. And we know that in this case, by using the Ohm's law, we will be getting V is equal to IR, or I is equal to V upon R. Now this is about direct current. Now even if you check after 10 minutes, you will see that the same amount of current is flowing. Correct? That is direct current. Whenever you connect a DC power supply, the current, when you get a steady current, the current remains constant. It does not increase or decrease. Of course, if you switch off the battery, then of course the current will stop. Okay, now that is about direct current. So what is alternating current? That is AC. If let us say we connect an AC power supply, so I am going to remove this DC cell and we are going to connect an AC power supply. AC supply is given by this symbol. Okay, that is a sine wave. So now we have connected an AC power supply. Okay, we still have a resistor R and we have connected an AC power supply now. Now what will happen? The current will not go in one direction. Means, let us say first current goes from A to B. Then after this cycle, the current will go from B to A. Again it will go from A to B and B to A. The current will keep on alternating its direction, and not just direction, even its magnitude. That means the current will slowly start increasing, reach a maximum value, then start decreasing and then reverse the direction. Okay, again it will go on decreasing to reach a minimum value, again it will go on increasing. Getting the idea? So that is alternating current. Now, the current that you are getting in your household right now, that is your fan, your tube light, your TV, all these are working on the alternating current. Okay, and of course I am sure you know why we use alternating current. It is because it is very easy to transport alternating current over a large distance, and we can use something called as a transformer. That means we can produce current at a higher voltage, and then we can reduce the voltage by using a transformer. So it becomes very, very safe to use. Okay, so because of these reasons, we are using the AC current in our households. Okay, so that is just a very brief introduction about alternating current. Now let us start with this chapter. Let us now understand the AC voltage. So I'm sure in the previous chapter you remember we had seen the AC generator. So when we want to create an AC current, what we do, we have a generator that has it has a rotating propeller. Okay, that propeller rotates the coil. So imagine that there is a power supply where the coil is rotating with angular frequency omega, right? And it is producing an AC voltage or AC current. So this voltage is represented on this graph. Now what do you see in this graph? The x-axis is omega t. Omega is the angular frequency and t is the time. So basically omega t is theta. Okay, that will give when that coil is rotating. Okay, what is the angle that it is making with the magnetic field? Don't worry too much about it. Okay, basically this is to show the time dependence of the voltage. Okay, the AC voltage. and the y-axis will show the voltage obviously. Now, so what we see, when time is equal to 0, voltage is 0. Then as the time increases, that means as the coil rotates, okay, because the coil is rotating with time. So as the coil rotates, the AC voltage goes on increasing. Can you see here? This maximum value, this is called as Vm, or maximum voltage or peak voltage. So remember, Vm, this stands for the peak voltage. Okay, peak to signify the maximum. Then what happens after it reaches the peak value? The voltage starts to decrease. Here voltage becomes 0. After that, it goes on decreasing further and we reach a negative value. So here this will be minus Vm. The magnitude of this will be the same as this peak Vm, but it will be negative. So that is what is happening in alternating current, right? The polarity is changing. So earlier we were getting a positive, means the current was going in one direction, then it reverses direction. So that is why it is given by the negative sign. So it becomes negative, okay, it reaches the maximum negative, then again it goes on increasing, becomes 0, it goes on increasing, again reaches the value, peak value Vm. Getting the idea? So whenever we are getting an alternating voltage, AC voltage, the value of voltage varies as a sine wave. Okay, this is a sine wave basically that we are getting. So we get the relation for AC voltage as follows. We get V is equal to Vm sine omega t. Okay, this relation is very important to remember. It shows that the alternating voltage is equal to peak voltage multiplied by sine of omega t. Okay, what is sine of omega t? Okay, this sine is coming because it is a sine wave function. Okay, so alternating current voltage is a function of sine. Okay, so as this omega t value will change, the value of sine will change, right? And that way we will get the alternating voltage. When it is pi by 2, omega t is pi by 2, sine of omega t will be 1. So we will get the peak voltage, that is V is equal to Vm. So this here, this represents omega t as pi by 2. Okay, so at pi by 2 you are getting Vm, peak voltage, right? When it will become 0, if this becomes pi, that is 180. So at 180 the voltage has become 0 because sine of pi will be 0, right? So on and so forth. So this relation, that is giving a relationship for the alternating current voltage. So now that we have got an expression for the voltage, let us find an expression for the current. So first we are going to see it for a resistive circuit. What is resistive circuit? We are going to connect one resistor of resistance, let us say capital R, to an AC power supply. Okay, a very simple circuit. This is called as a resistive circuit. An AC supply is connected to a resistor of resistance R. Okay, now because it is connected in this manner, we are going to get an AC voltage V and we are going to get a current I. Okay, that is going to go through this circuit. But now as we have seen, the voltage goes on increasing, decreasing, increasing, decreasing. Same thing will happen with current as well. So we need to find a different relationship for the current. How do we do it? Here is the method. We can write this V, that is the voltage, is equal to I, which is current multiplied by resistance. Now, how did we get this relation? We could have got this relation by applying the Kirchhoff's loop rule. Correct? The Kirchhoff's loop rule will tell us that the potential drop across that entire circuit is going to be 0. So V minus IR will be 0. That is how we understood this relation. So anyways, we got V is equal to IR. Here we have represented this by the symbol small I for a very specific reason, because it is AC. Okay, it is going to change. When we talk about Ohm's law, there we always represent voltage by capital V and current by capital I. But here since it is AC, we are going to use the small case. Just remember that. So again, we have seen previously how much is V? V is Vm sin omega t. So we will write this therefore as Vm sin omega t is equal to IR, or therefore we can write the current I is equal to Vm sin omega t upon R. Clear? Now you can see the current I also is a function of sine. Okay, This is Vm, the maximum voltage, which is a constant, and R, resistance, is also constant. So this term, that is Vm upon R, we can represent by another constant, and that is I is equal to Im sine of omega t. What is this Im? As you would have guessed, this Im is nothing but the peak current, the maximum value of the current that will go in this circuit. So just like voltage is a function of sine, similarly we get current also as a function of sine, with Im being the peak current. And how much is Im? Im is equal to Vm upon R, the peak voltage upon the resistance. Now we are going to plot a graph of voltage and current. Now pay very close attention to this, because in this chapter we are going to see these graphs many times. So again, this axis represents omega t, okay, and on this axis we are going to take two things, voltage as well as current. First let us plot it for the voltage. So how much is V? V is equal to Vm sine omega t. When omega t is 0, V will be 0. So this is the first point you are getting. One thing that I forgot to mention. Here I have plotted some values. Pi by 2, pi. 3 pi by 2, 2 pi. Whenever you are making these graphs, remember to plot these. These are basically showing the angles. Okay, very easy for us to plot the graphs then. Then when omega t becomes pi by 2, sine of pi by 2 will become 1. So V will become Vm. So what will happen is the voltage will go on increasing and reach a maximum value when at pi by 2. So this gives the maximum voltage Vm. Getting the idea? Then after it reaches maximum, we know the sine value. After sine 90, the value of sine will go on decreasing. Correct? So what will happen? The value of V will also go on decreasing. When omega t becomes pi, V will become 0. Why? Because sine of pi is 0. So we will get the graph will curve like this. Right? So from 0 we started, we went to maximum Vm. At pi, we again came back to 0. Then at 3 pi by 2, that is 270 degrees. At 270 degrees, sine of omega t will become minus 1. So V will become equal to minus Vm. So how much is minus Vm? Let us plot it here. So minus Vm will be here. So the graph curves like this. Right? Again, at sine of 2 pi, sine 2 pi will be 0, V will be 0. And the graph comes here. Is this making sense? Please make sure to try this on your own, then you will be able to plot the graph. And as the time moves forward, the graph keeps on alternating in this manner. Correct? When you are making this in the exam, up to 2 pi, it is more than sufficient. The teacher will be able to understand what you have made. Okay. Now let us plot it for the current, that is I. Now I is how much? I is equal to Im sine omega t. Remember, Im, this is equal to Vm divided by R. Correct? So the numerical value of Im will be less than numerical value of Vm. So peak current numerically will be lower than the peak voltage, because here it is divided by R. Okay. So what will happen for current? At sine omega t, when omega t is 0, current will also be 0. So current is still here. Correct? When sine omega t comes to pi by 2. So again, sine of pi by 2 is 1. I will be equal to Im, the peak current. So the graph comes here like this. And as you can see, Im is little bit lower than Vm depending upon the resistance. Then again, what will happen? At pi, the current becomes 0. At 3 pi by 2, we are going to get the same value. So here we get minus Im, and again it goes on increasing. Okay, so like this, we'll get the graphs. Okay, so this is a graph of current and voltage versus omega t for a purely resistive circuit. What is the meaning of purely resistive circuit? An AC power supply is connected only to a resistor. When that is the case, this is the graph that we are getting. Now, the things to notice in this. We notice that the current and voltage, they are in phase. Okay, we say that both current and voltage are in phase with each other. Why we are saying that? You can see when voltage reaches the peak value, current also reaches the peak value. When voltage comes to 0, current also comes to 0. when voltage goes to the negative maximum, the current also does the same. So they are moving together. Okay, that is why we say in a purely resistive circuit, the current and voltage, they are in phase with each other. Okay, I hope that was understood. I am sure that it is the first time that we are seeing something like this. So it might have been confusing, but that is okay and that is understood. Don't worry if you have found it to be little bit confusing, right? That is completely natural. Just make sure that you go through the concept again and also go through the textbook, and I am sure you will be able to figure this out. Now here is an interesting thing. So what you saw, current reaches a maximum value, then a minimum value, then maximum, then minimum, correct? So on an average, the current is actually zero. Okay, so in an alternating power supply, in an alternating current, the average current is zero. Similarly, the average voltage is also zero. So does it mean that no power was used? Does it mean that we did not use any energy? Obviously not. Okay, although the average current is zero. And remember this, it might be asked in the exam that over one complete cycle, how much is the average current in an AC supply? It is zero. Okay, jitna maximum ho, utna minimum ho gaya. So it is actually zero. But average power is not zero. So let us now find the average power in a purely resistive circuit. And why it is not zero? There is a very simple explanation for it. The power, once again, will represent by the small case p. Power is given by I square into R, right? And because it is the square of the current, correct? So square of 1 and square of minus 1. Square of minus 1 will also be 1. So therefore, because of this square factor, power is not zero. So that is why in our houses we are getting an electricity bill, because we are consuming power. Okay, so don't get confused by that fact. So let us now try to find the average power, because definitely we know average current is zero, average voltage is zero, but what about average power? So let us find the average power. So at any given instant, the power is given by P is equal to I square R. To find the average power, what we'll have to do, we will write the power like this. There is a bar put on P, that means it gives the average value. So average of P will be average of the term I square R. Correct? How much is I square? I square is Im sine omega t multiplied by R. Correct? Again, this I is from the previous AC supply. So I is we have written as Im sine omega t square. So Im square and sine square omega t R. Now, Im is a constant, R is a constant. So therefore, their average value will be the same. It won't change. So this term I can write as, we will take Im square outside, R outside, and only the average of sine square omega t. Okay. Now these brackets, basically these represent the average value. So what is the average value of sine square omega t? Average value of sine square omega t is 1 by 2. Okay, so sine square of the average of any sine square theta is equal to half. Now I will give you a very simple reason why it is equal to half. There is a big proof available for it, but let us not get into that. Why it is half, I will tell you. What is the maximum value of a sine function? 1. Okay, so sine square theta, the maximum value will be 1. And what will be minimum value? Minimum value will be 0. Minimum value will not be minus 1. Why? Because square. So even if sine theta is minus 1, square will be 1. So maximum value of this function is 1 and minimum value is 0. So 1 and 0, the average will be half. So that is why the square function, the average of sine square is half. As I said, this is a very simplistic way of putting it. There is a big proof available, but let us not go there. So what is average value of this? Average value is half. So therefore you get the average power as Im square R by 2. So you can see that average power is not 0. So therefore in a resistive circuit we do get power consumed. Okay, and how much power is consumed? The power consumed is peak current square into R by 2. So here is what we have learned. The average power in a resistive circuit will be given by Im square into R by 2. Now this is one way of writing it, but we can write it in a much more simpler manner by putting a new concept that is called as root mean square current. Okay, RMS. RMS stands for root mean square. Okay, so we will introduce a new concept that is called as the IRMS. What is IRMS? Root mean square current. What is root mean square current? Root mean square current is equal to the peak current divided by under root 2. Okay, so what this means? The square of IRMS will be equal to Im square by 2, which is a factor you see over here. Correct? Now again, this is a modification we have done. We have introduced something called as root mean square current. Root mean square current is nothing but peak current divided by under root 2. So square of IRMS will be Im square by 2, and you can see you can replace this quantity over here. So you will get average power as, what will be the average power? It will be I square, that is the root mean square current multiplied by resistance. And why this expression is important? This resembles our actual formula for power in a DC current. In DC current, power is given by I square R. Here in a in an AC current, the average power will be given by root mean square current square into R. Okay, so remember this expression properly. So once again, now we will write the power as average power is equal to root mean square current square into R. Or now we will represent this average power by directly capital P. Okay, so we will say capital P is equal to IRMS square into R. Okay, so this gives the power. Now just like we got root mean square current, we can also get root mean square voltage. So we can write VRMS as equal to Vm divided by root 2. Okay, or this is equal to 0.707 Vm. Similarly, IRMS we can write as Im by root 2, which is nothing but 0.707 Im. Okay, these things you will remember. Why? For 1 mark you can get these questions. That so much is the current flowing, what is the root mean square current, or what is the peak current. Another thing, why these terms IRMS and all is important. When you see any kind of transformer or any kind of electricity board you have seen in your house, there they would write 220 volt. Okay, so that 220 volt is actually the RMS voltage. Okay, the peak voltage will be somewhere around 300, 311 or something. Okay, so 220 into 0.707. So the values that we are given on the board, they are actually the RMS value, the root mean square values. Okay, so again this formula you will remember. Root mean square voltage equal to 0.707 Vm. Vm is the peak voltage. Root mean square current is 0.707 Im. Im is the peak current. Okay, now next we are going to see the concept of phasors. And using these phasors, we will be able to represent the graphs for resistive circuit or inductive circuit or capacitive circuit that we will be seeing next. Now, of course, the first thing we'll ask, what is meant by phasor? Okay, basically phasors they will help us to represent this kind of graph in a vector form. Okay, now what is a phasor? Take a look at this. This is a graph of voltage versus omega t. Okay, for an AC voltage. So this is the normal case that we had seen earlier, right? The voltage starts from 0, it reaches a peak value, comes to 0, reaches minus peak value. Okay, goes like this. It goes on forward. Now this voltage V, we are going to represent on this axis. Okay, the vector, the DC AC voltage, we are going to represent in the form of a vector, and that vector we will call a phasor. Okay, so obviously we know that AC voltage or AC current, they are not vectors, they are actually scalars, but that quantity we are representing as a vector. So please understand this small difference. Okay, now how does it work? So now you have to imagine this sketch pen, this is going to be my vector for voltage. Okay. At this point, how much is the voltage? Voltage is 0. And how much is the angle? Angle is omega t. So the vector V is going to be like this. Okay, and vector V we will represent by capital V. So right now this is where the vector is at omega t equal to 0. Then when omega t reaches pi by 2, you will see that the amplitude is maximum. So at pi by 2, the vector is going to be like this. Okay, you can see now the vertical part, okay, that is equal to Vm, the maximum, the peak voltage. Then as you reach pi, the vector turns like this. As you reach 3 pi by 2, the vector goes here. Okay, as we reach 2 pi, the vector comes back. So as the AC voltage is changing, as it is fluctuating, our phasor, that is the voltage phasor, will also move around this. Why it is going to do this? Because it will help us to understand this AC voltage in a better manner. Okay, this is something we are doing. By noticing the changes in the AC voltage, we are making changes in our phasor. Is that making sense? Okay, so at any time t, okay, the phasor is going to be maybe something like this, right? So let me draw the phasor over here now. So this is the voltage phasor, as I said. Now it is making some angle omega t, and this part, okay, the vertical part, that will be equal to Vm sin omega t. Okay, that is nothing but represented on this. So if you find on any instantaneous time over here, suppose, so this will be equal to this vertical length over here. Okay, so that is the meaning of a phasor. Now similarly on the same graph, you can make the phasor for current as well. Okay, so you will remember when we discussed for a purely resistive circuit. Okay, in resistive circuit what happened? As the voltage was changing, so was the current. So if I want to make the graph for current, I'll see that the current goes in phase with the voltage like this. Correct? So here we are making it for the current. This represents the maximum, the peak current. So current is in phase with the voltage. So if here we make a phasor for the electric current, that phasor will coincide with this, and this vertical part, that will be equal to Im sin omega t. So both the current phasor and voltage phasor, this is the current phasor denoted by capital I. So both current phasor and voltage phasor, they will move together. They will not have any phase difference between them for a resistive circuit. Okay, for a purely resistive circuit, this is the case you are going to see. Now once again, I know first time we are seeing this kind of concept. So if it is, you find it to be little confusing, I'll suggest you one thing, go through the textbook. Okay, the topic is given of phasors. Maybe that will make things more clear to you. Otherwise, the concept is very simple. We have the graph of voltage versus omega t. That graph is represented on a phasor diagram. In exam, you may be asked to make both of these or either one of these, or you may be asked to identify which is the correct phasor diagram. So for that, this knowledge is very essential. Next, we are going to see a derivation for a purely inductive circuit. What is a purely inductive circuit? We have an inductor connected to an AC power supply. What is an inductor? Inductor is basically a coil, okay, a solenoid coil, you can imagine. So we have a solenoid coil having self-inductance capital L, that is connected with an AC power supply, which is having AC voltage as V equal to Vm sin omega t. Okay, that is true for all the AC voltages. Now we want to find out relations for the current and for the power. So how do we do it? We are going to use the Kirchhoff's loop rule. Kirchhoff's loop rule, what it will tell us? Voltage drop across the power supply will be equal to voltage drop across the inductor. So we will get therefore V is equal to L di by dt, where I is the current. From where we are getting L di by dt? We are getting it from the Faraday's law that we saw in the previous chapter. Okay, the EMF is given by L di by dt, and because this is an inductor, so it is having self-inductance. Okay, that is equal to capital L. So don't get confused from where we got this, right? So we can substitute the value of V from this equation. Therefore, we get Vm sin omega t is equal to L di by dt. Let us rearrange this and write. So we will write, therefore di is equal to Vm upon L sin of omega t dt. To find total current, we will have to go for integration. Okay. So therefore we will say the total current I is equal to integral of di, which is equal to integral of this entire expression. But you know Vm and L, they are constants, so they will come out of the integration and we will get integral of sin omega t dt. What is integral of sin theta? Integral of sin theta is minus cos theta. Okay, so we will get current I equal to minus Vm upon omega L cos omega t plus some constant. Why this omega got here? Because it was integral of sin omega t. So integral of sin omega t minus cos omega t divided by omega. And as I said, there is some constant, but because this current is dependent only upon time, that constant comes to 0. So what do we get now? Current equal to minus Vm by omega L cos omega t. Okay, but this minus cos omega t we don't want, right? So what we are going to do? We are going to use this identity. What is that identity? Minus cos theta is equal to sin theta minus pi by 2. Now in this chapter, even in the next part, we are going to use many integration identities. So if there is any confusion, please refer to your maths textbooks for any of the identities. Okay. So again, as I was saying, we will replace minus cos omega t by sin of omega t minus pi by 2. So what do we get? We get therefore I equal to Vm upon omega L sin of omega t minus pi by 2. Now this expression is much simpler for us because now you can see current is shown as a function of sine. Okay, so we can very easily represent it as a sine wave. And we will make one more change now. What do you see over here? We see an expression Vm upon omega L. This is nothing but the peak current. So we will therefore write I is equal to Im, that is peak current, into sine of omega t minus pi by 2. What is this Im? This Im is nothing but Vm upon omega L. So in a purely inductive circuit, we get the current as Im sin omega t minus pi by 2. How much was the voltage? The voltage was V is equal to Vm sin of omega t. So what is the difference that you are seeing? You see that the current is lagging behind the voltage by pi by 2. Okay, so here they are not in the same phase. If you remember, in a resistive circuit, we saw both current and voltage having the same factor, that is sin omega t. But in inductive circuit, the current lags behind the voltage by a factor of pi by 2. So for an inductive circuit, we get the peak current as Vm upon omega L, right? We are going to use a new quantity that is called as inductive reactance. Okay, so this omega L we will write as XL. So therefore we will get Im is equal to Vm upon XL. Let me write it here so it is more clear. So Im we write as Vm upon XL. What is XL? XL is equal to omega L, and this XL is known as inductive reactance. Now what is inductive reactance? This quantity is very similar to resistance. Okay, so in a resistive circuit, it is the resistor which is providing opposition to the electric current. In an inductive circuit, we don't have any resistance as such, but there is a similar quantity, and that is the inductive reactance, which is represented by XL, and XL is equal to omega into L. Okay, the dimensions and SI unit of inductive reactance are the same as that of resistance. That is, SI unit of inductive reactance is ohm. Okay, same as that of resistance. So inductive reactance is what is going to oppose the electric current, and it is given by omega into L. The next thing we notice is the formula for the AC voltage and AC current for the inductive circuit. we saw that current is lagging behind by pi by 2. So this is how we will represent it on the phasor diagram. So here is the phasor diagram for inductive circuit. For a purely inductive circuit, we see that if this is the phasor for V, the current phasor is going to be behind by 90 degrees. Okay, so this is how you are going to represent it in the exam. Okay, don't get confused about it. This is very important. Similarly, this is the graph of voltage and current versus omega t. Again, in this graph, we can see that current is behind by pi by 2. How do we understand that? See, the voltage has reached peak value here. Okay, but what happens? The current is going to be behind by pi by 2. So after pi by 2, the current will reach the peak value. That means, see, here the current has reached the peak value after a gap of pi by 2. So this is what it means, that current is behind by 90 degrees or pi by 2. Here voltage was 0. Okay, after a time of pi by 2, the current also became 0. Okay, so always current will be following the voltage in an inductive circuit. Once again, make sure that you are seeing this topic very closely and reading from the textbook. Then it will become more